Okay, students, does everybody has everybody turned in their homework number 4? Oh, I've got a stack of them up here. Speak now or forever hold your peace. Okay, one more. Anybody else? Okay, good. Now, we've got a lot of stuff to do today. Uh, as you can see from the item 3 on our outline, we have exam 1 coming next Tuesday. Now that's going to be a couple problems, a few problems, and some multiple choice. And does anybody have a question about exam? Actually, wait a minute. We'll talk about exam 1 in a minute. Brandon, do you have your homework? All right. Before we get to the homework solution, can you be in charge of the homework pile? Okay, just collect it from Brandon and anybody else that comes in late. I'm going to hand back a stack of papers here, some of which is homework and some of which is quiz 1. And it's all alphabetized, looks like. Good. So I'm going to call, just last names. ABC, come on up here to the front, starting with Alvarez. That's Adriana Alvarez, right? Is Adriana? Okay. Okay, here's your paper. Derek Arjun. Okay. Brandon Bots, sorry. Anne Marie Blanco. Okay. Matthew Brown. Okay. DEF, come on up here to the front. Kyle Casaza. I don't have I don't have everybody with AB. So if I'm past your name, then you can sit down. I still have a bunch to do. Kylie Casaza. Cole Von Kaufman. Cole Kaufman. This thing's hot. Must be fireproof paper. Mark Cucciaresi. Deloria S. Is that? Oh, hold on. I want to make sure. Sarah. Okay. Daniel Dolman. Okay. Christopher Dulgy. Joshua Eason. James Engelmeyer. James. Move it. GHIJKL. Come on up. Mitchell Fairgrieve. Oh, you're here today. Good. Anastasia Gabazova. Abby Gardner. Daniel Goldman. Maya Gunderson. Julian Hurd. Colby Hill. Colby. Okay, he's absent. Okay, that's all the H's. Okay, you're Colby. Okay. That's everybody up through H. I still got a bunch of grades, just a few more, so that if I passed your name, then I'll be turning those in to you on Thursday. Christina Johnson, JKLM, last all the way up to M. M for magnificent. Come on over here. Trevor Kidd, Jennifer King. Okay. Nicholas King. Anne-Marie La Maison. Noah. Ryan Liu. Andres. Martin McCarthy. Marty. Sean McCormick. Adante McFadden. Adante McFadden. Oh, okay. Andrew Menendez. Alyssa Malia. Trayan Mystery. Abayomi Mabalade. Taylor Moraguez. Sean Mueller. Okay, NOPQRS. Thomas Von Oakley. Flavio Ortiz. Flavio. Okay, here you go. Jacques Perizot. Better. Cecilia Pavoni. NOPQRS. Cecilia. Robert Pamichter. Chris Kvach. Ray Rajkumar. Ray. Okay, there you go. Delane Russell. Are you here? This is like 5 weeks ago, but there you go. Christina Salyers. Okay. Christina Salyers. Yep, you got another one. Alex Santiago. Okay. Okay. S through the end of the alphabet, and if I bypass your name, that means it still needs to be graded. So you could sit down. Alex Santiago. Austin. Very good job. Alex Shum. And Alex, here's another paper for you. Natalie Sneed, 2 for you. Tommy Sukavong, 2 for you. Sierra Stevens. Sierra. Kathan Stombaugh. There you go. Vashak Svoboda. Vashak Svoboda. The man of freedom. Absent. Montana. I got 2 papers for you. Alexander Varga. Vote on. I think I got 2 for you. On vote. Caitlin Walker. I got 2 for you. From the NCCs. Joshua Wall. 2 for you. Kirsten Wright. Kirsten. Joshua. Good. Only 1 paper without an owner. All right. The rest of you guys. You can sit down. The rest of you guys. I still have a bunch of quiz 1s to grade. Oh my God. I'm going to try to make. I'm sure you all want to know about this. I'm going to try to do a little bit better job grading faster on this homework 4, and also exam 1. It's just too slow what I've been doing. Those of you that didn't get your quiz 1 back yet, which is a few of yous, I still have a bindle here. Let's see. This is Form D. It's these pink ones. I still have this pile to do, so I'll be getting to you. Now, a couple things I want to mention before we continue, and it's a continuation of a theme that we've talked about a few times after quiz one. My expectations are high for this class, and so exam one is going to be difficult, and but I think you're going to do work more efficiently on exam one, and I think because you've been doing more homework. I mean, the difficult part of exam one, the problems. And you're going to know that you have to work efficiently. Like last time, I think quiz one caught a huge number of people napping. Well, no, I should say napping. Unprepared for mentally unprepared for what they needed to do. And so there was a lot of crashing and burning, as I've mentioned. Now, you're going to study a little bit harder, and you're going to study more efficiently and better for exam one, so I'm not worried about that. And I have some study tools that I'm going to roll out this week to prepare you for exam one, some study problems that I make. Oh, I was going to, let me pause the podcast. I want to show you an exam from the past. Hold on. Okay. Okay. So we're going to do a multiple choice item here. Turn your clicker on. And now that everybody has turned in their homework, I have a question for you, please. Which rope failed first? "15 seconds to vote. 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Can you guys make a count? Wait a minute. We better check to see if anybody voted for E. Nope. Nope. Actually, you know what? Let's do that one again. I just want to see it. I should give you, I want everybody except E a chance to. All right, so let's do that one again. Revote. Hit the refresh key. And this one, type in a letter and hit the send key. And this way I can give everybody. Ten seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
I got 87.
All right. Now, let's go over the solution for that. All right. So, can you switch me over to the document cam, please? Okay. Sam, I'll get to your question. We're going to do the quiz one solution too. Okay. First thing you want to do is draw a free body diagram. Okay, it's got to be fairly good size, so I'll just put a dot right about here to symbolize the center of mass of the Ferrari. And then just for bookkeeping purposes, I'll put a horizontal line and a vertical line through the center of mass, just so that I can draw just so that I can draw a nice 45-degree arrow here. Okay, so this is rope 2. So this is tension 2. And then I don't know which one's going to be bigger. So I'll write this one bigger. And this one's going to be dipped about like that. And that's rope 1's tension number 1. And this is 45 degrees here. And what was this? 20, 29. Okay, and this 29 degrees up here is the same as this one down here. Okay, so I haven't written the ceiling in of Wile E. Coyote's garage, but all right. So there's your free body diagram. Oh, one more force, and let's write this one about this long. Now the thing about this force, this is the weight force. This is m times the acceleration vector g. The thing about that, and this is something, and here's my thumb, so I can't cover it up. The thing about this, the length of this arrow has got to be equal to the y component of T2 plus the y component of T1. Now, unless you actually measure these things out on a computer, it's hard to do it by hand. But I kind of eyeballed this in as about the same height, the same length here downward as a little bit of this and a little bit of this over here for T2 and T1. All right. Now, why do I say that that has to be the same length? Because it's at rest, so we use the equilibrium conditions enunciated by Professor Isaac Newton. And I'll do the y's first. You can do it in either order. The sum of all the Fy's, or the y components of all the constituent forces, the y components of constituent forces, in other words, all the separate little forces that together add up to 0, this has to be equal to 0. And for us, the y components, now I'm going to do things in the Dr. Brickner method. We talked to a student in office hours that was doing ups minus downs. But I'm going to do vectorness. Okay, so T1, let's do a sub-diagram over here for T1. Okay, so 29 arrows here. T1 magnitude here. So here's T1y. So that's T1y. Well, I'll just write it this way. T1y plus T2y. They're both up. And then I have a minus 9.8 meters per second squared times 1050. Is that right? Okay, kilograms. Okay. All right, now this is my downwardness is encoded in that minus sign. Right now, I'm going to put some sines and cosines in here for T1 and T2, T1y and T2y in the next step. Now, supposedly this stuff has got to be equal to 0 if it's equilibrium. All right, and we're going to use that to solve 2 equations and 2 unknowns. All right, so let's do a little bit more trig here. So this one is T1 magnitude times the sine of 29, and then T2 magnitude times the sine of 45. So I'll just write square root 2 over 2 on this one. That's an easy one. Plus a negative. Now, what's the magnitude of this baby? 102, 10,290? Okay. 10,290 newtons equals 0. Now, if you look at that, that is now an equation in 2 unknowns, all right, that we want to figure out. Let me put on my specs, my X-ray specs. All right, so we want to calculate the tension magnitudes. So B, this is A, this is a free body diagram. So T1 and T2 in task B is to figure out this guy and this guy, okay? Now we need another equation to do that. So let's get the sum of the X forces, the sum of the X components. And I'll just write this one out. Okay, now T1X is negatory. Okay, so and I'm gonna focus on the inner triangle, so or the inner angle. So I'm gonna put a minus T1 magnitude times cosine of 29. Now the alternate to that is if you think about this angle all the way around the over the pole and back down to the T1 vector, that's 151. And now let me turn on my computer, a little calculator, and let's type in cosine of 151. And you can see that that's a negative. Can you see that? Kind of. There you go. So that's a negative number. And so you can get the negative sign that way. So if you'd put in T1 regular without the minus sign and then cosine of 151, you'd still get a negative number over there, which is the main thing. So, and as I've said, you know, there's different ways to tackle these triangles. Cosine 45 degrees. And this one is equal to 0. Okay. Now, the thing that I did in my solution is I used this, you know, here's my second equation in two unknowns. So let me write down. Now I have two equations in two unknowns, T1 and T2, and those are my objectives. All right, so now all I have to do is, you know, maybe do elimination or determinants, but I think substitution is pretty easy off of this baby right here. So let's see, T1 cosine 29 degrees is equal to T2 times square root 2 over 2. That's the cosine of 45. And so T2, you could do it either way. T1 is equal to square root 2 over 2 divided by cosine of 29 degrees in parentheses times T2. So there's your substitution. You could do the other one. T2 equals the inverse of this quotient here times T1. All right. And so basically you're home free now, because then you can substitute it back in into sum of the y's into the y equilibrium constraint. And so let's do that. Okay, so the first part is T1. So let's write square root 2 over 2 times sine of 29 degrees over cosine of 29 degrees, and that's tangent of 29, of course, times T2. Right, so there's my substitution. And then I have my regular T2, so this is square root 2 over 2 times T2. Right, and that's equal to 102.90 newtons. Now, oh, you know what? I want to express a beef. I have a pet peeve for some of you that I'm not going to name, and I'm not even going to look at anybody, but there's some of you that write this for the letter T. lowercase t. Do not do that because it looks like this for addition sign. All right. Now you know who you are. A few of you, anyways, do. And I don't think I may have taken points off actually because it's hard for me to understand what the heck you're doing. So I especially if you use this in a subscript, which I don't, it's kind of, anyway, so that's a little side note commentary. All right, so here's my nonsense here. So this is basically square root 2 over 2 times the tangent of 29 times T2 equals 102.90 newtons. So let's figure out what that is. Did I forget what? Oh yeah, plus 1. So 1. Uh-oh. I just violated my own rule. Let me rewrite this. Okay, square root 2 over 2 times 1 plus tangent of 29 degrees. There we go. Times T2 equals 102.90 newtons. But this is considerably neater than many of your papers, and I'm doing it in ink. So one day you'll be able to do that as well. All right, so tangent 29 plus 1. So that's 1.5543 times cosine of 45. Okay, so this is 1.09906 times T2, and that's 102.90 newtons. So inverse that, then multiply by 102.90, and that's so that means that T2 is equal to 9.9363 newtons. So I'm going to round it off to the nearest newton. All right, so there's my first unknown that I figured out. And is this a bad one? Rope 1 has a maximum tension rating of 10,000. Okay. Rope 2, this one definitely breaks. All right. Now, let's check the value of T1. So T1 is equal to square root 2 over 2 times the inverse of cosine 29. So I'm sure you can carry these around symbolically and looks like tangents and some cancellation, but we'll just, calculate it like maniacs. 93, 63 newtons. All right, so let's multiply that by cosine 45. Do you guys get the idea that I sometimes give you breaks? You don't get the idea? No, whenever you see a 45 in there, anything with a 45-degree tilt, that's me giving you a break. One of my many breaks. So this one's okay, but, so we now have everything done. The rope that fails is number 2. Wile E. Coyote's device breaks, and in fact it breaks catastrophically. We have a cascade because once this string breaks down here, Then all you got left is this one, rope number one. But rope number one is only got a max of 10,000 up here. And the weight force now that's the only thing holding it up against gravity. So bam, that thing swings downward, and as soon as it hits vertical, bam, that thing breaks too. So you have a catastrophic failure. And you know what? That is what Wile E. Coyote is famous for. Seeley. 7.5. Yeah, I didn't clear I just kept everything inside my calculator, so I have a million digits in there. This is close enough for Seeley. It's close enough for government work, and when I was looking at some of these homeworks, I saw some 75, 60 somethings. I saw a few 75, 70 somethings. I saw a few 75, 50 somethings. All right, so it's I didn't specify how many digits to give me in the final answer. And the main thing is what we're trying to do is if it's this far above the braking strength, 75, 50 something, 75, 60 something, 75, 70 something, that's going to break. So, you mean like this? Yeah. If it calls for it, you know. Because remember, I always think visually. So I'm always thinking about stuff like this diagram up here at the top, and then these diagrams down here. That's how I think about it. But that's not. I saw a student that calculated this perfectly without drawing a single diagram. So it's possible. All right. Now here's my notes. All right. So look at this. Assume each rope has infinite strength. So when I was fooling around with this, I just said, all right, let's just assume each rope has infinite strength, and then figure out what it would take. You see here's 75.69 over here, 93.63 over here. And then I said, all right, so I'm going to set I originally had my T2 max set at 8,000. So then I said, all right, let me change that to 7,500 newtons, and then this will be the one that fails. So this was a planned disaster for Wile E. Coyote. But that's how I decided that. Can you give me that stack of papers over there? Yeah, the whole pile there. All right. Now, I want to go to the Jello problem now. Let me see if I can find my solution for it. Okay. You put it back over there. All right, so let's take a look at this. This is the solution form for Form A and Form C. And let's go through this step by step because I want you to see how I solve it. So this is the, what do you call it? The Ferrari problem. From quiz 1. Okay, so quiz 1, and those of you that had the bag of money, make notes. This will be helpful for you too. So there's a swimming pool right here out in front of this parking garage, and that's never, I don't think you usually see that for normal parking garages, but this is Hollywood. And so there's a little blob of Jello in here. And so this is the roof. And this distance, I'll put my distance marker down here, 13.2 meters. for this distance. And then the height of the roof of the garage is 22.5. Right? And so your Ferrari is up here, and it's going in this direction. It's going off the roof. Okay, drawing my arrow here. All right, so there's your specs. Now I'm going to draw in a little tangent line up here, tangent to the roof. And the reason I do that is because Tanis, when you drive off the roof, your initial velocity is straight horizontal. Now I'm going to the left here, and I've got all that encoded in my math here. Okay, so there's my V0. That's my launch velocity. Now we don't know what it is yet, but we do know that it's straight horizontal. I saw a ton of people draw in this triangle, figure out the tangent of this angle, and then use that for the launch angle. No. I saw some people drawing downward arrows, like this, toward the launch. No, you don't do that. This thing, you have to see, you have to think about what's actually happening. What is actually happening? And the minute that thing clears the roof, the second that it clears the roof, its velocity is horizontal. And what that means is, since V of 0, we don't know the magnitude yet, but we do know it has to be horizontal. This point, let's see, what point did I call that? L. So this is point L. And I also made L my origin, 0, 0. L can be considered the apogee. And then here's the back half of the baseball problem. Right, so your parabola starts out horizontal, then it goes right down in there. Okay, so let me put a little arrow down there. Okay, so there's the direction of motion. Okay, so Vx of 0 is negative because it's left. Okay, now some of you guys turned it around and did a mirror image of that problem. You launched it. You put your parking garage over here to the left, the pool over to the right, and then you did everything with positives. That's fine. Vy of 0, however, is equal to 0. Now, we don't know what the magnitude of Vx is yet, but we're going to get it. Now, I want to emphasize something to you, and I want you to write it in your notes. Every simple physical problem, like this is a simple physical problem. Every complex problem can be analyzed into simpler problems. Every simple problem will have at least one distance scale and one time scale. Let me repeat that. Every simple problem, like a baseball problem, will have at least one distance scale and one time scale. Now, let me ask you this. Remember that as a problem-solving tool. What's my time scale? What's my distance scale? Is there one? Can I identify it? So let me ask you this. What is a time scale that you can use for this kind of a problem. Sean, I can't hear you. I'm not, okay. Sean just answered seconds. That's not what I, that's a unit of time measurement, and it's a time scale. But what I'm thinking of, the system itself has it could be like 2.9 seconds or 100.773 seconds. And so compared to a similar problem on the moon, things evolve much more slowly on the moon because G on the moon is much smaller. It's a sixth of Earth's. All right, so that's just the time scale. So what physical measurement here determines a time scale? Julian, repeat? No, not the horizontal distance. No, that's a formula. The horizontal distance doesn't give you much of a time scale because Vx doesn't change. There's no such thing as horizontal. Do you know I had to write no such thing as horizontal gravity on a few papers? They had in their equations of motion for this, they had a GT squared in the x of t equation. Yeah. Y position equation? No. No. Give me an object or a measurement. Something about this physics. I mean, because everything has a equation of motion for y and equation of motion for x. Sean. Gravity? No, that's a concept. Something about this that, Kathy. Height of the building. The drop time. What else do I call it? I call it the rise time. In this case, it's a drop time because it's going off the cliff. Right? Another time scale that you could use if it were a full baseball problem, hang time. That's from one base of an equilateral parabola, baseball problem, to the other side. Right now, for the rock off the cliff, you could still use that as a time scale, the rise time, because the rock off the cliff problem did have a rise time. Okay, but that's a more complex problem. So you have a bunch of different time scales, but definitely the drop time. So drop time equals total time for this problem. Now, some other problem, maybe not. All right. And so let's figure out the drop time. That's basically, okay, my drop is 22.5 meters, and that's equal to 1/2 times the absolute value of G times T squared, because I'm ignoring the minus sign here. Simple drop distance formula. So this is 4.9, 22.5 meters equals 4.9 meters per second squared times T squared. So T squared is equal to what? It's about 4 point something. So it's going to be about T squared is, what do we got? 4 point something? 4 point what? Anybody verify 4.587 seconds squared? So the drop time is the square root of that. So that's 2.143. And I actually saw a lot of people that didn't do well on this problem. They did get this, but then they were kind of flailing. with other equations. You know, by the way, what is the equation of motion? The equation of motion is not, the equation of motion is an x of t equals something and a y of t equals something and a z of t if you have z's that you have to worry about. You know, the other equation, the other word for equation of motion is time evolution equation, and you can apply that to any physical quantity that's changing over time. So I never want to see x of 0 equals a bunch of stuff for equation of motion. All right, we're going to write this down in just a second. Okay. Now, so I saw students that got this drop time, but then weren't able to use it to get anywhere in the equations of motion. So what do you have to do to get, what don't we know? We don't know the initial velocity, Vx of 0. We know Vy of 0 is 0. We definitely know that. But we don't know this one, and it's got to be negatory. All right? So how do you figure that out? Yeah. No, you don't use x of t for this. Well, you don't have to. Vx of 0 is a constant. It's leftward. It's a negative number of meters per second. In other words, what is your name again? Sean? Colby. Colby Hill. Colby, you don't need to use the equations of motion for this. It's something you can do. Well, you can't quite do it in your head, but how do you figure it out? We got everything we need. Vx of 0 is a constant. What are you mumbling about back there? No, you. No, you. Yeah, you. Not x of t. We don't want x of t. I mean, not yet. We want to get Vx of 0 because Vx of 0 goes into x of t. Equation of motion. How do you find Vx of 0? Come on, some of you did this on your paper. What? The range equation. I don't even know what the range equation is. The range equation is something that looks like this. V squared sine squared theta over g or something like that. But I don't. Yeah, Aaron. Flavia. Ding, that's it. Right. So 13.2. So Vx of 0 is the distance you travel. 13.2 meters per second, or 13.2 meters, divided by 2.14 seconds. And that comes out to 6.16. And it's actually got to be negative. So let me put a minus sign there. And let me put a minus sign over here. Okay. And now, Colby, we can start plugging everything into the equations of motion because now we got everything we need. All right. So now x of t, generically speaking, there's your equation of motion. Now, some of you wrote that down, and I accepted it because you used this number later in your calculation and you used it properly. But what I was hoping to see was this. For x of t. That's it. All right. That'll get you 13.2 meters to the left of the roof in the time it takes to drop 22.5 meters. All right. Now, y of t. Generically speaking, Vy of 0 times t plus 1/2 gt squared. How much is this one right here? Vy of 0? 0, because it's a flat vector up here. All right, so we don't even have to write that down. And then we know what 1/2 gt squared is. That's negative 4.9 meters per second squared times t squared. All right, so there's a significant part of your problem. All right. Now, you can also write down your initial conditions at this point, because you've got those all. I mean, you could have already done them. Let me erase this nonsense. I don't, what I try to do is remember a few formulas as simple as possible and build up what I need from that. So I tend not to memorize problems like that. And I saw some students, here's the other one that I saw. I'll do it on the back of this paper. I saw some students using this thing. Something like that. Is that a formula in the book? And I never use that formula. And in the book, I said I don't even like using it. And but actually in free fall, you can see that this is like a 1/2 mv squared and a mgh. If you replace the a with g and the d with h, it's it's kinetic energy and potential energy. But I saw some students using this and they weren't using it right. And so, and unfortunately, I don't teach about this one. So you want to try to, it's nice if, I did see a couple of students use this properly. They practice with it. But I saw some other students that really didn't know exactly how to work this one out. So, it's hard to give points for something like that. But let's write down the initial conditions. The IC, x of 0 equals 0, 0.0 meters. Y of 0 equals 0.0 meters. Vx of 0 equals negative 6.16 meters per second. And Vy of 0 equals 0.0 meters per second. Now, so here's another part of the tasks that you were supposed to do. This is 2 points. I changed my grading on these. In the handout, it says 4 points, but here I decided to make it 2 points. All right, and then this was 5 points up here. This is 2 points for all of that. And really what I was looking for was this down here, because I think everybody has different. I wasn't really checking this stuff up here, because there's a lot of variation on how people did that. All right, now, Gabby, I know you still have a question here, and I'm about to re-answer that. Christina, do you have a question immediately? I don't know. I don't use the range equation. I don't know. Maybe you could work it out with He seems to I could think about it over the weekend if I have some time. But the range equation it involves. Let me toss this. Hold on. Oh my goodness. It can't be killed. Okay, it's dead. Yeah, you could probably use it. I guess I'm not. I'm showing you my way of doing it, and the textbook problem. The textbook. They probably have something like this in the textbook, and the range problem you could probably, because it's if I'm not mistaken, what is it? Is it V0? Is it Vx of 0 squared or Vx of 0?
V squared sine 2 theta over G.
What is it now?
V squared sine 2 theta over G.
Yeah, V squared sine 2 theta. So that's got trig. We actually did some of that trig identity. I remember we did cosine theta. That's it. It's Vx of 0 times Vy of 0 divided by G. I think that's what it is. That's right. And then for the and then if it's for a Ferrari problem, if it's a baseball problem, it's 2 times that. So because it's the full hang time for the range. So it's so that range. See, this is why I say I always think of the simplest version. I'm thinking in these terms right here. These are the simplest ways to describe the system. Instead of, Christina, I think of a problem. I think of a formula like this one, and that the range formula that Giannis suggested as specialty formulas. And since I'm lazy, I don't want to memorize. Kirsten's laughing over here. Since I'm lazy, and all scientists tend to be lazy, I want to remember the fewest number of formulas and then work from there. And that's what we're doing here.
Yeah. Is there another way to find V0x, the initial velocity for the x?
Well, that would do it. I mean, if you have the range and V0, because it's basically a bunch of V0. Oh no, I guess you couldn't do that because you don't have the sine theta. It's not. Well, the problem with that one is also it's not launching. It doesn't have a launch angle, and that tripped up a lot of people as well. For some reason, there were people in here that had 60 degrees for the launching. And you can do the thing. So some of you I marked down because you figured out the arctangent of 22.5 over 13.2, and then used that for your theta. But this is not launching at an angle. It's launching flat. And even if it was, now there was one student that knew how to do this on the bag toss problem. All right. And they did it, they did the rectangles and stuff. And you can actually do the rectangles on this one too, if you think about it. But this one, having a launch angle, Christina, for that, V squared sine of 2 theta over G. What happens if you don't have a theta, which is the situation you've got here? But if you know this stuff, if you think in terms of, the time scales and stuff, then you can put it together. So you got to go further back in time to a more primitive form of what you know, and then build it up from there. And I mentioned before one time when I was in calculus, when I was an undergraduate, a little bit further along than you guys, I was in Calc 3, and it was tough. And I remember, and we had a take-home midterm. And I remember working with some buddies of mine. They weren't physics majors, so they were like econ, so they couldn't even help me with it. So, but we were all working in this one place. It was really nice to study and stuff. And I'll never forget, I figured out how to do it because I went back to the definitions of derivative in 3 dimensions. And that's how I figured that. And I think I was about the only person in the class, this calculus class, to get that problem. So sometimes you got to go back in time, kind of like the flux capacitor.
I want to interrupt you, but I have a question just like after that.
Okay, good. All right. So the last thing that we want to do is, let me put my earpiece back on here. The last thing that we want to do is try to figure out the velocity at impact. Now, I'm not going to draw the velocity up here, but I will draw it down here as soon as I get the components. So Vx of t is a constant. So we already have that. All right, so that's a nice one. Now Vy of t is changing. It's equal to Vy of 0 plus the acceleration g times the amount of time. All right, so there's an equation of motion for the velocities. And this is a constant here, but this one evolves over time. And Vy of 0, of course, is 0, so you don't even have to worry about that. But formally, that's the equation of motion in free fall. In this specific case, we have 0.0 meters per second plus a negative 9.8 meters per second squared times 2.14 seconds. All right, and so that works out to negative 21, I believe. Negative 21.0 meters per second because it's also downward. Okay, now a nice way of graphing this is, I'll show it to you right here. The ratio here between negative 21 and negative 6 is about 7 to 2. 7 divided by 20, 21 divided into 7 is 3. 6 divided into, wait a minute, 21 divided by 3 is 7. 6 divided by 3 is 2. So this is a steepness ratio of down 7 and over 2. So this is what your velocity vector would look like. Tilt angle negative 73.7 below the y-axis, or below the z-axis, the negative z-axis. You could draw a sketch like this, or just write it down this way. All right, with the I-hats and the J-hats. Or you could write it down this way. You figure out the magnitude, you know, a squared plus b squared equals c squared. The magnitude is 21.9 meters per second. The tilt angle is 73.7 degrees below the x-axis. So any of these three is good. All right. And I'll be posting this on the this stuff here will be in the YouTube, and this stuff here I'll PDF this and post it in web courses, so you have two slightly different versions of the same problem. Now, as for pointage, when I'm over here grading, and if I write an X, that means that, like on initial conditions, -2. But if I go like, you know, like equations, you really mess them up, but you kind of have one thing right. You know, this would be a -5 if it's only an X, but sometimes, okay, they got part of the X equation right, so I'll just put like -3 instead of all the points off. Okay, and if I have a check mark, that means perfectamente. All right, so does that make sense, Gabby? Looking at your more sense, yeah. So another thing that I'll do is, if you're, since I'm trying not to, you know, completely annihilate everybody, if you have a lot of, if you struggled a whole lot with this and, you know, you just got hardly anything right, I'll look like to maybe have a good diagram. I'll put like a +1 for a good diagram, or maybe, you know, something like a +1 down here if you have the angles right or something like that. So if you see a plus something with a circle around it, that means that I'm trying to give you a point. But God bless you. If there's no way for me to give you any of those, then you know you get zip. But those days are past. Nobody's going to be getting zip zaps on exam 1. I have a feeling. Yeah, Colby. No, 5. This is my, I changed it. This up here was 4, 5, and 3, and I decided to change it to 2, 5, and 5. So yeah, and that rhymes with the other, and it's righteous, I think. So this one was actually, I think this one was actually easier than the money bag toss, my opinion. But you could form your own opinion about that. You'll be able to see both solutions in web courses. All right. Now I want to take a break and from uh, speaking, and I want to. Can you bring up the document? No, the computer, please. Computer. Okay. Okay. Let's take a look at. Let's take a look at this discussion area. Okay, centripetal acceleration data. Now, every group was supposed to turn in their spreadsheets here, and I had Tyler look before class, and I checked a couple of them yesterday, like the besties um, and the team DADs, and then all these guys down here, group 12, Justin Kuhn. Group 12, is that the name of your group? The Mad Lads. So take a few minutes now, and if your group hasn't turned in their spreadsheet, go ahead and do so now. Let me go down here and look. I can see quite a few of them. Spectacular 3, the Infinite 3, Sierra Stevens, and the Infinite 3. Nice. Rohan Martin, Spectacular 3. Wait a minute, you're in here twice.
Yeah, because the first time the charts didn't show up, so you have to re-upload.
Okay, so ignore Derek's.
Yeah. When you uploaded the same charts didn't show, so I had to re-upload it. It's fine.
The Jumping Mandalorian Nitros back table. Who still hasn't uploaded theirs? I want. Go ahead and can you upload it now? Just one for each group. Okay. Anybody else over here hasn't uploaded? Okay. Just get that done real quick. And
I didn't go to the school.
boy, this looks terrible. Look at this. Look at the size of these formulas. You can't. Yeah. All right, you guys got it? You got it? Okay. All right. All right. The Flying Mandalorians. All right. Uh, Tyler, can you see if there's a folder or something over there? And if not, go get one from Ray. A folder for these. You know, an envelope. Do you? Oh, okay. Can I have it? Here you go. Can you put that in there for me? I'll put this stuff in here. Mitchell Fairgrieve, are you here? Did you put his stuff in there? Mitch, did you get that homework from like number 2 or whatever it was? I'll be grading all these. So you have the weekend off from grading. All right. Okay, students. What we're going to do is start working on some problems from chapter 6. So take some notes. Let's go back to the document camera. And as always, I'll embed these. All right, let's do a Ferrari centripetal force problem. And our constraint is going to be the Nardo ring, the circular track. Okay, so what that means is that, let me put on my specs. It means that we've got, let me make a nice big circle here, 6 by 6. All right. So draw yourself a nice big circle. Tangent to each edge of a square that's twice the radius. Okay, so here's R. And go ahead and park a dot up on the first quadrant somewhere. So there's our vehicle. Tangent to that, to the circle at that point is our V. Perpendicular to that and straight back towards the center is our centripetal acceleration vector. All right, now let me draw a picture. Now this is a flat track, so let's write down flat. We're going to do the Nardo ring in a second, a banked track. All right, so I'll draw a picture of the car from behind. Here's the Ferrari. Here's the back window, which is, for Ferraris, that's pretty much all you get to see a lot of times, unless you're driving a Lotus. All right, so let me put a great big ginormous dot here to represent the center of mass. Okay, so this is my Ferrari. And the mass is equal to 1050 kilograms, which, I spent about, when I was writing this that homework problem, I spent about 20 minutes looking up the mass of different models of Ferraris, and that's definitely a mass for an F40, which is a nice rig. Anyway, so let's put a dot down here now. Okay, and let's write down the forces acting on this Ferrari. So we have some upward normal force from the track, and we have the same size weight force. And this is the rigidity force, normal to the track. From the rigidity of the track, W plus N vectors add up to 0. But we don't have equilibrium here. We have an unbalanced force, and that basically, please don't talk over me, fellas. That basically comes from the roadway. So go ahead and draw in the roadway. You're still talking over. You're still competing with me. Don't compete. When I'm doing this, I can hear you guys all the way from where you are. Okay, and I don't want, some people in here have difficulty with distraction, and I'm one of them. All right, so please, I'm not the only one. Now, we don't have equilibrium. We have some gription, some friction from the track. Okay, and that's going to be your centripetal force. So let's draw a little tiny arrow here to the left, kind of mimicking here that it's to the left of the velocity arrow. So here's your frictional force. So the frictional force that's the restraining force. In other words, that's what keeps it on that. If you were on a railroad track, the centripetal force would come from the rail. But this one, you can steer on a track, and in that case, the frictional force. Now, the law for frictional force is that it is proportional to whatever the normal force is. And in this case, it's proportional to mg. Now, these are magnitudes only, okay? And so we're going to call this positive 9.8 meters per second squared in this example only. And you can have, and mu is known as the coefficient of friction. Okay, and in fact, let me look in here. let's see. I think, yeah. Can you switch over to the computer for me while I find this? Okay, so here's a. I hope you've skimmed this stuff already. Here's kind of a microscopic view of a rough surface. The rougher the surface, the more friction you have, and that means that you have this factor mu, which is the coefficient of friction. Now, the static friction and kinetic friction are different. If it's in motion, it's called kinetic friction. That's what we've got. But here are some of the, here's a few diagrams and whatnot. But here's some of the static and kinetic frictions. So if you look at this, it depends on the two surfaces. Let's see if I can make this bigger. Oh, I can't. Let me think. How do you do this on a... All right, let's get that back down here. See if we can look at this table. All right, that's a little bit better. Okay, so rubber on dry concrete, static friction 1.0. In other words, it ain't moving. Kinetic friction is a little bit less. So once you get it going, you have a kinetic friction coefficient of 0.7. Now look down here. Ice on ice, 0.1 and 0.03. Steel on ice, 0.4 static, 0.02 kinetic friction. All right. So the slip, here's Teflon on steel, 0.04 both ways. All right. Steel on steel, oiled. So this is like the mechanism of a machine, a lubricated machine. 0.05 and 0.03. That's pretty good, actually. But look at it, steel on steel, dry, without lubrication, a disaster. All right? But if steel on steel is oiled, so like if you have a rifle or any kind of, or a bicycle, and you oil it up, you lube it up good, it's going to really be smooth. But if you don't, it's going to be a mess. All right? Bone lubricated by synovial fluid. Oh, that's like your knees and stuff. That's pretty good, actually. It's the best of all of them. That beats Teflon. All right, so those are coefficient of frictions. Can you switch me back to .cam? All right, so basically, if you're, and we're going to be using a kinetic coefficient of friction, and basically it means this, that it's the higher it is, the less slippery it is. And it depends on the two surfaces that are meeting. So rubber on concrete, that's a tire, all right, on a concrete roadway. All right, so that means you get plenty of friction, and that means you can turn a tight corner. Now, if you have wheels made of Teflon, you can't turn a corner for jack, because so let's say mu subscript k is equal to, let's say, 0.4 for tires on this track. But mu subscript k equals, 0.04 for Teflon tires here. Okay, so it's a disaster. And the reason that that's a disaster is that the friction that you can get out depends on the mass of your object, basically, through this mechanism right here. So if you have a small kinetic coefficient of friction, you can't get much newtons. You can't get many centripetal newtons. All right. Now let's work this out for this one here. Okay. So for normal tires. All right. So mu is 0.4. So let's figure out F. And this is going to be our centripetal force. Let's just figure out the magnitude. And the reason I'm doing magnitudes here is because it's going to be constantly changing direction and stuff. And we could deal with that if we want to, but let's just figure out the magnitude. Question. Well, I might give you like a little mini table on the cover page, or I'll say, like I do here, the coefficient for tires on rubber is 0.4 or whatever, or tires on a track, 0.4. No, you will have to memorize that. I don't memorize it. If I don't memorize it, you don't have to memorize it. All right, let me get my specs. Ah. All right, so this is equal to mu times mg through the normal force, through this mechanism over here. So that's equal to 0.4. Now this is a dimensionless quantity, okay? So you just multiply it by 1050 kilograms times good old, and we're just going to go magnitudes now, so 9.8 positive. All right, so this is equal to 0.4 dimensionless times 10290 newtons, which is what, 4,000 something? What is it? 4,116? This? Anybody verify? Okay. All right. Now, so that means that F net, let's write out a full F net equation. It's equal to capital N, normal force, plus capital W, weight force, plus little f, friction force. All right, now these two cancel. If it's a good track. If it's a track made of jello, then the answer is no, but here, yes. Okay, so 0 plus f, comma, centripetal. So that's kind of a generic way to write towards the center, no matter what part of the track you're on. Okay, so it's equal to 41. So let's write down F net magnitude, 4116 newtons. And that's equal to m v squared over r. That's the geometric formula for the centripetal force. All right. Now, let's say that this track. Let's do another thing here. Say that the track radius is 100 meters. How fast can you go? Right? So on a 100-meter track, a 100-meter curve, so that's like out at Daytona, for the Daytona 500 and stuff. So what you would do is 4116, and I'm going to change this to kilogram meter per second squared. That's the same as a Newton. And then 1050 kilograms times v squared over 100 meters. All right, so you can obviously figure out v squared. So let's figure out. And actually, we could have, see this stuff over here is mu mg magnitudes. So, and this is m over here. So we could have used mu g if we wanted to. That would be even easier. In other words, cancel the m's. Anyways, this is what we got. So 4116. Let's cancel kilograms. And we get meters squared per second squared times 100 from from cross multiplying divided by 1050. Okay, and that's v squared. Okay, so my units that remain are meters squared per second squared, so that's good. That's the square of a speed. So what do we get here? About 400. Okay. Anybody else? 392? 392 point what? Let me verify that. Nobody's verifying me. 4116 times 100 divided by 1050. 392 even. That's not a perfect square. That's close to one though, I think. 289, 376, I think is the next one. So this is, what is that anyways? Square root of that. 19 point. So V is equal to 19.8 meters per second. Okay, so there's your, Sean, you got a question? What's that? Yeah. We're not, it's accelerating. The only unbalanced force is the friction, right? Nothing. That's why it's turning, right? It's always perpendicular to the motion if you have good tires. Now, if you hit, and this is at uniform circular motion. Now, if you hit the gas, then you got to start working in three dimensions. Okay, so this is kind of an idealized view where you're not accelerating, you're on the circle, but you're keeping the speedometer steady. Now, this speedometer, that's about 40 something miles an hour. Multiply that by 2.24. What do you get? Meters per second times 2.24 is miles per hour. 44 miles an hour. So that's a pretty good speed. You couldn't do that going around a turn, from University onto Alafaya, for instance. That's too tight of a turn. But at 100 meters, right here, that's a racetrack size turn. So even though what this tells me, these tires aren't very good. But if you can bank it, you get even better efficiency. Because then the normal force, then you get some of the weight force helping. All right. Question. Hold on. Colby Hill.
So is our friction the friction that's, I guess, stopping us from going off our circular path, or is it the friction that's slowing us down on the circular path? Like, is that why you have it?
It's friction perpendicular. Look at the diagram. Look at the circle diagram. The friction force is perpendicular to the velocity. So it doesn't speed it up or slow it down. And that's what I was just saying to Sean back there. If we had something speeding up, then we'd see this is the X direction, say, and the Z direction straight up in the air. This is X and Y. If we had some speed up or some slowdown, we'd have a little bit of tilt here, and we'd have to work in three dimensions. And that, my friend, would be a pain in the buttocks, as the saying goes. But yeah, I mean, it's perpendicular. So, and yes, it is the force that keeps the car on a circular path. Okay. That's a centripetal force, centripetal acceleration. Right? If you suddenly activate Teflon tires and raise up your rubber tires, now you've got zero friction. You're just going to go straight off into the fence, or pretty straight off into the fence. You won't have much friction. Question on Vol.
How did you get the formula of FNet before I use whatever?
Here, or here, or here. This one? Well, this is the net force that we've set up from here. Okay. So some track force, some weight force, and a little bit of tire friction force. And then this is just the plain old, anytime you're on a circular motion, uniform circular motion, then you have mv squared over r. Now, let's go to the next page. And if you don't have uniform circular motion, you can still handle it. Go ahead and draw yourself an x and a y axis. And instead of a circle, let's draw an ellipse. So this is 4, 4, 3, and 3. So this is no longer, it's no longer symmetric in all directions, but it is tangent. Now, as we're going to see when we study gravitation, there's a point here called the focus. There's another one over here, symmetric. And the sun, for orbiting planets or ellipses or comets and stuff, the sun is not at the center, but it's at the focus on one end. Okay. Now, the forces here are very different because the forces are always, they're always, here's a big one. So if you're right here at perihelion, the force is straight back towards the sun. Out here at aphelion, as far away from the sun as you can get, so this is like apogee, but with respect to Earth, you have a very small force out here. And if you take some intermediate point, like right here, I'll just call it letter I, the force is still back towards the sun, but it's between it's medium size, so it's going to look like, maybe about like that. Okay, so this is intermediate point, neither aphelion nor perihelion, and it has a medium-sized force. Okay, so in this case, now up here, let me do a blow-up of intermediate point I. So intermediate point I looks like this. Here's point I, and let's make the force back towards the sun. So here's the sun back here. And I'm going to draw in blue a tangent to the ellipse at that point. Okay, so that looks pretty good. So there's my tangent line. Okay, and if this thing is orbiting counterclockwise, my velocity is going to look like this. So there's the velocity vector at V of I, at point I, this intermediate point. So this is a blow up here of this one up here, right? And so here's this is the force of gravity. Okay, and we'll be studying how to handle that. But basically, it's always back towards the sun. Now, Abby, you were asking me about this last time, and this is a case where you have a path and you have a little bit of stuff centripetal to the path and some tangential. All right, so draw in relative to your tangent line at point I, draw in a perpendicular dashed line. So this force, you can now draw in components tangential and centripetal by making this little right triangle here. Okay. And you can see that the centripetal, so here's F centripetal, here's F tangent. So this is F centripetal and this is F tangent over here. And so you can see that the tangent force, the tangent component of the gravitational force is against the velocity, so it's slowing down. F tangent is anti-parallel to V at position I, so it slows down. And of course, FC is perpendicular to VI, so it changes the direction. Okay, now Colby, this would be a tough one to work out, because you've got, at every point I, the force is a different direction and a different size. Also, the tangent line is completely different at any point. So this is why they have half the PhDs on the planet trying to figure out. So they got to do this if they want to land on this comet or asteroid that's orbiting on this ellipse, they got to figure out where it's at, and then they got to do the same thing for their spacecraft, right? And it's pretty tricky. But you could do it, just and in the old days, in the days of hidden figures, the human calculators, they did all this stuff by hand, using big, ginormous trig tables and stuff. And they did it, and they put John Glenn in orbit, and they got him back safe where they wanted him. It all worked out. Question. What is your name again? Ryan. Brian. Abreu. Okay.
Is it still accelerating towards the center?
It accelerates toward the sun. The net force, that's the only force you have basically in space, is the gravitational. It's always from your object back toward the sun, or from your satellite back towards the earth. Like the moon back towards and that keeps the moon on a centripetal force. The moon's orbit is pretty close to a circle. Not perfectly, but pretty close.
But you said it slows down as it gets further away?
Yeah, it does, and it's really going slow out here at aphelion. It's really pokey. The force of gravity is perpendicular there to the path, but it's lost all of its speed. It's kind of like, Brian, at the top of top of a parabola, top of the baseball parabola, the very top, that's where the motion is slowest, right? You keep all your horizontal speed, but now at the top, that's all you got. All right, so
how does it come back if it's lost?
it turns around here. See, over here, it's always got a force pointing back towards the sun. So this is as far as it gets. So you can think of this as like the top of the parabola. It's an ellipse, so it's not a parabola, but it's a turning point, just like the top of the parabola is. All right. We'll get to that in a few weeks when we talk about gravitation. Seeley. No, the sun is not at the origin. It's at the focus. This is the origin here, 0, 0. The focus is out here to the side. Go back and look in your trig books. You'll see all the formulas for. And I know that a lot of you love your trig books, and you have many of them in your personal collections. Not. But anyways, if you go to the library, dig out a trig book, and you'll see, all the equations and stuff. I'm not going over that. But this is a problem where you can do everything that we just did. All right, you can do everything that we just did with this frictional force being the centripetal force, Sealy, but in a gravitational basis on a gravitational trajectory. So, you don't have a track, you don't have any, you know, it's quite a bit different situation, but that would be the centripetal force right there. You could calculate that. What? No, man, I just told you that there's like a million PhDs in Houston trying to do all this stuff, programming computers to do this. So, yeah, right. Sealy, high expectations, but this would even for you guys, that would be in the future. But I mean, you could do it. You guys have all the tools. Well, almost all the tools for it. All right, let's go to the next page. Let's do a banked. So this is page 4, 218. All right, so let's talk about a banked curve. All right. So let's see. Let's do a real gradual. Okay, so this is 1 to 5. So the tangent of theta is 1/5. What's the inverse tangent of 1/5? Like 18 degrees or something. What is it? 11.3. Okay, so let's say that we have an 11. So that's the bank angle. All right. And let's say that we have the Ferrari up there. The unstoppable Ferrari. There's the back window. All right, here's the center of mass. Now, the problem with this, or the variation here is the bank, right? Because what that does is it makes the normal force a little bit different than when you're on a flat track. Gravity and normal force are exactly parallel and they're anti-parallel if your track is flat. But once you get nothing changes about the gravitational force. So basically what you've got here is some downward weight force, and then try to gracefully sketch in for reference. There's your ramp angle. Okay, we're not going to need that except to draw in something perpendicular to that. So okay, so there's your perpendicular axis. So your normal force is going to be, here's what we've got to have. We've got to have vertical equilibrium. Some of the Fy's have got to be 0 because we don't want to move off the track. All right. So that means that the normal force the y component of the normal force has to be 3 blocks down, same length as the weight force. So that means your full normal force is right here. Okay, so there's your N. All right. And so let me draw a component triangle, a nice big one. 4, 8, 10. How about if I use a ruler? Okay. So this is theta. We already know that. It's 1 to 5. This is N. This is Ny. And that is equal in magnitude to mg because of the equilibrium condition. Now this one, Nx, all right, that one is equal to, that is centripetal, all right? So now, in this case, your net force, if these are, now this is without friction, all right? So this is Teflon. This is how fast can you go on a Teflon track with Teflon tires, no friction, all right? If this is the only centripetal force you have, how fast can you go? Let's figure it out, right? So this is the same, the mass is 1050. The weight force is equal to 102.90 newtons. This is kilograms. We know what the tangent is and stuff. So let's figure out. So the normal force, N, Ny is equal to 102.90 newtons. Okay, and so now this is 5 to 1 with an x. All right. So what is 1002.90 divided by 5? That's 2058. Okay, good. All right, so Nx equals 2058 newtons. Now, what did we have on the previous one for centripetal force, flat track? We had okay, so this is less than friction of previous page. Okay, but we don't have, this is on a Teflon track. Teflon on Teflon, no friction, in other words. All right, so this is the only centripetal force. But can you keep this car on a circular path? Yes, you can. So if you drive the right speed, it's going to be fairly slow because this is fairly small here. On a 100-meter curve, you can stay on the track. Even if you don't have any friction. Even if you're using Teflon on Teflon. Okay, so Kirsten, let's take a look at this. All right, so uniform circular motion. So let's just say it's just, uniform circular motion. So that means that the force is mv squared over r. And we know what m is. We know what r is. We've already done that. And that's going to be equal to, in this case, 2058 newtons. All right. Let's figure out what v is in this case. So v squared is going to be 2058 newtons times 100 meters divided by 1050 kilograms. And so that's v squared. So let's figure out what that is. That's going to be about 2, isn't it? 2058. Let's see. 2058 times 100 divided by 1050. 196. Oh, that's a perfect square. That's 14. So v squared is 196 meters squared per second squared. Anybody verify me? Okay, so v is 14. Okay, and so what was the previous one? 19.8. Okay, so this is a little bit slower. But faster than Teflon tires on a flat track. That's zip zap. I mean, well, you get a little bit of friction from Teflon on Teflon, so you could probably go like about 0.1 mile per hour or something like that. This one's not bad. So this one shows you the advantage of putting a bank. That's why those guys at Daytona, when they build those tracks for NASCAR and stuff, they put a bank on it so they can keep going at a high speed. But they don't really need it on a flat track. They don't really need it on a straightaway. Because on a straightaway, you don't have to have any centripetal acceleration. You're not turning. So you just put the hammer down and you get to maximum speed. But you're on a loop of some kind. So you got to put the brakes on. The less brakes you put on, the faster you get there, the more chance of finishing first. So that's why they bank stuff. And has anybody here ever driven on a banked or ridden in a car on a banked track? Do you get nervous?
It's not comfortable.
I would feel like really nervous in that because some of those stock cars they're banked like almost 45 degrees. It's insanity.
Daytona is,
Really?
Daytona is, I want to say somewhere between like 20 or 30.
It's insanity. All right. So I forgot to move my slides. You want to switch me over to the laptop, please? Okay, students. Start working as many problems as you can in Chapter 6. Examples, problems, and stuff, especially the ones that I make note of or highlight. Also, I will try to figure out what format I'm going to use, time interval, and so forth, and I'll tell you about that on Thursday. Okay, you're dismissed. You want to bring this down a little bit? Yeah.
On the quiz with the grading,
Yeah.
I was wondering how I got to when it's marked.
Minus, yeah, you don't have any velocity.
You'd have only the 3 points, and out of 12 points?
No, it's 5, 2, 5, and 5. Remember I said I changed it to 2, 5, and 5?